Welcome back to the deep dive. We are taking the densest stack of sources and building the ultimate intellectual shortcut just for you.
And today we are definitely buckling up.
We really are. We're getting into an exploration of warped space-time, the deep mechanics of gravity, and really the career of a singular figure who somehow managed to master theoretical physics.
While also basically redefining scientific accuracy in Hollywood blockbusters. It's an amazing combination.
It is. We are diving deep into the life and work of Kip Thorne, born in 1940.
That's right. He's an American theoretical physicist, a Nobel Laureate, of course, and a prolific author. His legacy, really, it rests on his ability to take the most, outrageous predictions of general relativity.
Things like black holes, wormholes.
Exactly, gravitational waves.
Yeah.
And he made them not just understandable, but empirically verifiable. He helped prove they were real.
Okay, let's unpack that for a second. We're looking at a physicist who co-authored Gravitation, which is, it's considered the definitive textbook on general relativity.
The Bible of the field, yeah.
Yeah. And then this same person turns around and serves as Christopher Nolan's personal scientific oracle for films like Interstellar.
Right, the duality of his career is just staggering.
So our mission today is to track the intellectual threads that connect his foundational academic work to these boundary-pushing theoretical concepts, and then all the way to his profound impact on mainstream culture.
That's the goal. Our sources give us a pretty comprehensive overview of his primary contributions. So we're talking about the physical reality of gravitational waves, the geometric definition of what a black hole even is, the bizarre requirements for wormholes, and the sheer intellectual lineage he built through his mentorship.
So we're really tracking a career that was defined by simultaneously building the tools to test Einstein's theories.
And exploring the absolute limits of what those theories would even permit. It's a fantastic duality.
And we have some serious aha moments coming up for you.
Oh, definitely.
First, we're going deep into the engineering secrets of LIGO. Specifically, how Thorne solved one of the biggest noise reduction problems using quantum mechanics years before the detector was even fully built.
And then we have the hoop conjecture.
Right. We're going to nail down the exact, beautiful geometric calculation that elegantly defines a black hole. It's so simple when you hear it.
And finally, the really wild stuff. We'll explore the bizarre physics required for a traversable wormhole, which, it necessitates the existence of matter that literally pushes space apart.
Before we jump in, though, let's get that initial identity snapshot.
Okay. So Thorne is known for his work in relativistic astrophysics and general relativity. He co-founded the Laser Interferometer Gravitational Wave Observatory, or LIGO.
Which led directly to the 2017 Nobel Prize in Physics.
Yep. Key concepts he developed include the Hartle-Thorne metric, the hoop conjecture, which we'll get into, and the fundamental physics required to stabilize wormholes.
His identity is, I think, maybe unique in that it bridges that deep, deep academic rigor with the absolute broadest cultural influence you can imagine.
It's hard to think of a parallel.
It really is. So that's quite the mission. Let's start at the source then. His formative academic years and how he built the foundation for this revolutionary career. So part one, the formative years. Kip Thorne was born in Logan, Utah, back in 1940, and he was born into an environment that, it feels like it was designed to foster this incredible intellectual curiosity.
It really does. His father was a professor of soil chemistry at Utah State University, and his mother, Allison Thorne, was an economist. And she holds a pretty remarkable distinction herself.
What was that?
She was the first woman to earn a PhD in economics from Iowa State College.
Wow. So this was a deeply academic household from the get-go.
Oh, completely. 2 of his 4 siblings also went on to become professors. He was just in the air. Thorne himself was, identified as a prodigious talent really early on.
He got recognition in the Westinghouse Science Talent Search in high school, right?
He did. And that really set him on a fast track to, the nation's top technical university.
He earned his bachelor's science from Caltech in 1962, and then he just immediately jumped into his graduate work at Princeton. The speed of his ascent there it's just remarkable.
It is. He earned both his Master of Science and his PhD by 1965. So he completed his doctorate at just 25 years old.
25. That kind of pace suggests he was already operating at the absolute forefront of the field.
He was, and he was working under the best of the best. His doctoral advisor was John Archibald Wheeler.
The man who coined the term black hole.
The very same. A towering figure in physics who famously helped revive general relativity research in the post-Einstein era. And this mentorship was pivotal. It really shaped Thorne's whole approach to gravity as, fundamentally, a problem of pure geometry.
And his dissertation, Geometrodynamics of Cylindrical Systems, I mean, that title alone signals he was diving deep into the curved structure of spacetime right from the start.
Exactly. After Princeton, he didn't stay away from Southern California for long. He came back to Caltech in 1967 as an associate professor, and then, incredibly, was promoted to full professor of theoretical physics by age 30.
30, one of the youngest in Caltech's entire history.
And later, he held the institution's most prestigious theoretical physics chair, the Richard P. Feynman Professorship.
That appointment, it wasn't just about his personal brilliance, was it? It was also a recognition of his ability to, build an intellectual dynasty.
That's a great way to put it. Over his decades at Caltech, Thorne personally mentored something like 50 physicists who got their PhDs there.
That's a huge number.
It is. He established this formidable intellectual lineage in general relativity and relativistic astrophysics, which ensured his concepts and his methods were carried forward by the next two generations of researchers.
That really is the mark of a true academic leader. It's not just about solving your own equations, but fostering the environment where the next equations get solved.
Right. And this brings us to a really crucial transition. In June of 2009, Thorne resigned the Feynman Professorship Emeritus. He stepped back from the administrative and the full-time teaching duties.
But that wasn't a retirement in the way we normally think of it. It was more of a pivot.
A conscious pivot, yeah. He shifted his focus to writing and movie making. He was driven by this deep commitment to communicating science to the public.
He's just so good at it. Thorne is widely noted for his extraordinary ability to convey the excitement and the real significance of these discoveries to both professional audiences and, well, us, lay audiences.
Whether it was on PBS or the BBC or in his best-selling books, he saw translating that complexity as a necessary extension of the research itself. You haven't finished the job until you've explained it.
I think we sometimes forget just how much heavy lifting is required to make general relativity and black hole physics accessible without, dumbing it down.
He nailed that balance.
He really did. And speaking of balance, we have that wonderful anecdote that sort of explains how this academic titan became a Hollywood consultant.
Right, and it involves his friend, the legendary Carl Sagan.
Of course it does.
Sagan set Thorne up on a blind date with a woman named Linda Obst, who would later become a major film producer.
And while the romance didn't last,
the friendship did. And years later, that connection, that friendship, led Obst and Thorne to develop the core scientific concept that would eventually become the Christopher Nolan film Interstellar.
So that one blind date set up by Carl Sagan basically created the template for how you accurately integrate high-level physics into popular media.
It's the ultimate butterfly effect moment in pop science history. It really is.
Just to round out the personal profile, our sources note that while Thorne was raised in the LDS faith, he now identifies as an atheist.
Right, but he maintains a very broad and inclusive perspective. He stated clearly that there is, and I'm quoting, no fundamental incompatibility between science and religion.
And that stance, it just reflects the whole theme of his career, doesn't it? Finding bridges where other people might only see divisions.
Absolutely. He showed that the search for scientific truth and the appreciation for, universal complexity, it should transcend these narrow categories. His career proves that the most beautiful, most outrageous concepts of the universe are worthy of being shared far beyond the walls of academia.
And that work on the nature of gravity and geometry, it leads us directly to the achievement that secured his place in modern history, the thing that led to the Nobel Prize.
The successful detection of gravitational waves through LIGO.
Yes. This is the ultimate proof that Thorne could translate this incredibly dense theoretical physics into world-changing experimental engineering.
This is truly his most impactful achievement in a practical sense, even though his background was so heavily theoretical.
So LIGO, the Laser Interferometer Gravitational Wave Observatory, it was a monumental undertaking.
Monumental is the word. Co-founded by Thorne, Rainer Weiss, and Ronald Drever way back in 1984. And the sheer scale of it is just difficult to grasp. Our sources note it as the largest single enterprise ever funded by the National Science Foundation.
What kind of money are we talking about?
Capital investments near $300 million. And that was just for the initial build.
And the fundamental goal was just revolutionary. Build an instrument so sensitive it could detect the passage of a gravitational wave, a ripple in spacetime itself, by measuring a change in length between its two arms.
And these fluctuations are, they're ridiculously small, often less than 1,000th the diameter of a proton.
So why did Thorne, a theorist, throw his weight and decades of his career into this massive engineering problem?
Because detecting these waves was the final, critical, and long sought-after confirmation of general relativity's dynamic nature.
Yeah.
And as a theorist, Thorne's role went way beyond just advocacy or fundraising.
Right.
He specialized in predicting the gravitational wave strengths and their temporal signatures.
So he was basically translating the theoretical math of, say, two colliding black holes into the exact signal the detector should be listening for here on Earth.
That's it, exactly.
But I want to focus on the engineering side of his work, which I think is often overlooked. We think of him as the black hole guy, but a theoretical physicist designing hardware features.
And that's what he did. He provided essential theoretical support and engineering design analysis for features of LIGO that were just.
Right.
They were fundamentally limited by the need for unprecedented precision.
Meaning you couldn't just build them through trial and error in a lab.
Exactly. The theory had to come first.
Okay, so let's unpack two major technical highlights that show this duality between theorist and engineer.
First, a comparatively simple one, but absolutely critical. He designed the internal baffles that are used to control scattered light inside the enormous kilometer-long beam tubes.
Why was that so important?
Well, any scattered light introduces ambient noise. And given the insane precision they required, any stray photon just bouncing around could completely overwhelm the minute signal they were searching for.
The fact that a Nobel-caliber black hole theorist had to calculate the optimal geometry for, basically, light shields, that speaks volumes about the project.
It does. It shows how every single detail mattered.
But the most serious hurdle was always noise reduction, wasn't it? The sheer difficulty of hearing a whisper in the cosmic roar.
It was. And this is where Thorne made a truly profound theoretical contribution, collaborating extensively with Vladimir Brzezinski's research group in Moscow. They focused on combating two main forms of noise.
Let's start with the non-quantum one first.
Okay, that would be thermoelastic noise. This comes from the subtle, random temperature fluctuations within the massive detector mirrors.
And these mirrors are the heart of the machine.
The most important and most delicate component, yeah. As the temperature of the mirror material randomly shifts, even just a tiny bit, it causes the material to expand and contract.
And that movement is indistinguishable from the signal of a passing gravitational wave.
Exactly. So you're dealing with noise caused by the heat of the device itself, and it's all happening at a scale we usually just ignore completely.
So how did Thorne use theoretical physics to solve this engineering problem?
He proposed and developed what are called quantum non-demolition designs for the advanced detectors, specifically tailored to manage this thermoelastic noise.
Quantum non-demolition, what does that mean in practice?
It's essentially a system where the act of making a measurement doesn't contaminate the measurement itself. You don't disturb the thing you're trying to measure by looking at it.
And this leads directly to the ultimate quantum physics hack, the back-action evasion approach. This is a concept that's pretty difficult to grasp. Can you help us understand the core challenge here?
The challenge boils down to the Heisenberg uncertainty principle. When you try to measure the position of a quantum object, like the position of that mirror, with extreme accuracy, the very act of measurement introduces what's called quantum back-action.
It disturbs the momentum of the object.
Right. If you try to measure the mirror's position accurately enough to see gravitational waves, your uncertainty in its momentum grows, and that uncertainty feeds back into the system and just obscures the signal. The mirror starts vibrating purely because you're trying to look at it too closely.
So the noise isn't coming from outside, it's coming from the fundamental rules of the universe itself.
Precisely. And Thorne, along with Carlton M. Caves, invented the back-action evasion approach. It's a technique that lets you accurately measure one specific property of the system, in this case the mirror's position, without being impacted by the corresponding uncertain property, its momentum.
So they found a way to evade the quantum consequence of their own measurement. It's like finding a loophole in the uncertainty principle for specific variables.
It is a loophole. Brilliant one. And it was a critical theoretical breakthrough that went far beyond LIGO. It influenced the entire field of quantum optics.
And this decades-long, painstaking work, all driven by this deep theoretical insight, eventually culminated in success.
It did.
This is where it all pays off. In September 2015, LIGO recorded the signal.
Yes. On February 11th, 2016, the collaboration officially announced the first direct observation of gravitational waves.
What did they see?
They had detected the signature of two black holes, each about 30 solar masses, colliding and merging 1.3 billion light-years away. The event itself lasted only a fraction of a second.
Resulting in a single high-frequency chirp.
That's the one. And that faint chirp confirmed a key prediction of general relativity, and it marked the birth of an entirely new field, gravitational wave astronomy.
The recognition, of course, was the 2017 Nobel Prize in Physics, which he shared with Rainer Weiss and Barish.
And that prize wasn't just for detecting the waves. It was for the 4 decades of groundwork, the theoretical calculations, the specialized math to analyze the data, and the engineering blueprints like those quantum noise reduction techniques that made the detection possible in the first place.
Thorne demonstrated that for the most ambitious physics problems, theory and engineering have to be inseparable. That segues perfectly from detecting black holes to actually defining them. Kip Thorne is one of the world's foremost authorities on black holes, and he spent a huge part of his career defining their geometry and their behavior.
He did, so this is part 3. His conceptual breakthroughs in understanding what exactly makes a black hole a black hole.
Where did this intellectual path start for him?
It started with a deep geometric puzzle when he was a PhD student. His mentor, John Wheeler, challenged him with this really complex thought experiment.
Okay.
If you take a cylindrical bundle of repulsive magnetic field lines, could the gravitational attraction between them ever overcome their own repulsion and cause the system to implode?
That's fascinating. So you have these internal forces pushing out, but gravity is still pulling in. The math on that sounds nightmarish.
It was complex, but Thorne proved a major theoretical point.
Yeah.
Cylindrical magnetic field lines cannot implode gravitationally.
So that forced him to confront the boundary condition. Why do spherical objects like stars collapse completely under gravity, but this cylindrical configuration does not?
Exactly. The difference had to lie in the geometry of the compression.
So the boundary for collapse isn't just about mass. It's about whether that mass has been compressed uniformly in all directions.
Precisely. This whole exploration led him to formulate the incredibly elegant and powerful Hoop conjecture in 1972.
This is arguably his core theoretical idea for defining a black hole without having to solve Einstein's super complex field equations for every single scenario.
Right. The core realization was that the gravitational force can only overcome all the internal pressure when an object has been compressed in all directions. It has to be equally squashed in the X, Y, and Z axes.
The elegance of this is what's so crucial. It simplifies an immense mathematical problem. So how did he quantify that uniform squeeze in a geometric way that you could actually check?
He defined it by a critical circumference. The Hoop conjecture states, any object of mass $0 around which a hoop of circumference $4 GMC2 can be spun must be a black hole.
Okay, let's spend a moment on that formula. $4 GMC22. What is the geometric significance of that specific circumference? Why that number?
Because it's the circumference of the event horizon. If you remember the Schwarzschild radius, 3 on P a dollar, which defines the radius of a non-rotating black hole.
Right. That's 2 GMC2 total.
Exactly. And the circumference, $2, is calculated as $2 3m. So if you plug that Schwarzschild radius into the circumference formula, you get do dollars UT2 GMC2, which simplifies to $4 GMC2 total.
Ah, I see. So the Hoop conjecture is a purely geometric statement. It's saying that if an object shrinks in every direction until its circumference is smaller than the circumference of what its event horizon would be, then collapse is inevitable.
That's it. It's no longer about the internal forces. It's about that geometric ratio of mass to size. It provides this really intuitive definition that is independent of all the complex physics happening inside the object, the pressure, temperature, density, whatever.
It's just a simple geometric metric for something incredibly profound.
Exactly. It's a statement about geometry, not about specific physical properties.
So beyond the Hoop conjecture, Thorne also pioneered the development of theoretical tools to help us analyze black holes after they've formed. And this is where the membrane paradigm comes in.
It does, and it sounds highly conceptual because it is.
What is it?
It's an unusual but very powerful theoretical tool that he developed with his students. See, when you try to model a black hole mathematically, you're dealing with a singularity and a pure mathematical boundary, the event horizon, which just complicates all the conventional equations.
So what does the paradigm do?
The membrane paradigm bypasses this by treating the event horizon not as a mathematical line, but as a metaphorical, thin, physical surface, a membrane that has properties like electrical resistance and viscosity, like a fluid.
Okay, hold on. If the event horizon is really just pure vacuum, a point of no return where space-time bends infinitely, why would we treat it like a viscous fluid? Isn't that just wrong, or does the approximation hold up?
It holds up mathematically as a very useful approximation. It allows physicists to apply conventional physics and engineering principles, things we already master, like electrical resistance or fluid dynamics, to study a region of pure vacuum. It makes the mathematics manageable.
So it converts these really difficult general relativity equations into tractable electrodynamics or fluid equations that people can actually solve.
Precisely. And that conversion provided immense insight into the behavior of black holes in a real astrophysical context.
Like what?
The membrane paradigm was instrumental in clarifying key astrophysical mechanisms, most notably the Blandford-Znajek mechanism.
And that mechanism explains how black holes can power some of the brightest objects in the universe, like quasars and active galactic nuclei.
Exactly. How does a pure vacuum object generate that much energy? The membrane paradigm helps show that the rotational energy of the black hole gets extracted by magnetic field lines interacting with that viscous event horizon membrane.
The rotating black hole acts like a giant dynamo.
A giant cosmic dynamo, yeah. It uses the magnetic fields threading the horizon to launch these powerful relativistic jets of plasma outward, and that's what creates the quasar's immense energy output.
That ability to translate impossible math into manageable, visualizable concepts, that's the hallmark of his genius. He also ventured into the quantum statistical mechanics of black holes, looking at black hole entropy.
That's right. Collaborating with Wojciech Zurek, he investigated how the macroscale object of a black hole relates to all the microscale quantum possibilities.
And what did they find?
They demonstrated that the entropy of the black hole, its measure of disorder and information content, is the logarithm of the number of ways that hole could have been physically constructed.
Which strengthened the link between thermodynamics, gravity, and quantum theory.
It was a huge step in that direction.
And finally, let's revisit that very specific, almost counterintuitive detail about the maximum spin of a black hole. 0.998, that feels like a very precise boundary condition.
It is a critical and precise boundary. Working with Igor Novikov and Don Page, Thorne deduced that the maximum spin a black hole can have in nature is 0.998 of the maximum spin that's theoretically permitted by general relativity.
And this limit is achieved when a black hole is doubling its mass by sucking in matter from an orbiting disk.
Yes.
But why not 100% of the maximum? Why does the universe stop the black hole just shy of the absolute limit?
Because as matter spirals inward towards a maximally spinning black hole, it radiates away its energy. If the black hole spins too fast, the matter that carries the necessary angular momentum to speed it up, well, it can no longer fall in. The excess angular momentum is effectively carried away by the photons that are released near the horizon.
And that 0.998 boundary is crucial for measurements.
It's crucial for every stellar mass black hole measurement made by instruments like LIGO. We know exactly how fast they can possibly be rotating, all based on Thorne's theoretical work from decades ago.
Okay, so if the last segment was about defining the concrete physical limits of black holes, this next segment is about smashing the theoretical limits of spacetime itself.
This is where it gets really fun.
Part 4, the outrageous legacy. We're covering wormholes, time travel, and exotic matter. This is the truly mind-bending part of Thorne's career.
This is where he fully embraced what he called Einstein's outrageous legacy. He began investigating whether the established laws of physics would permit spacetime to be multiply connected.
Meaning a state where shortcuts like classical traversable wormholes could actually exist.
Right, and the possibility of a traversable wormhole is mathematically linked to the possibility of creating a time machine, or what physicists call a closed time-like curve.
And the moment you introduce time travel, you introduce the grandfather paradox. How did Thorne, this super rigorous physicist, deal with the logical inconsistencies of paradoxes?
His work offered a fascinating defense against them. His more recent calculations suggest a kind of self-correcting universe. He hypothesized that simple masses passing through these traversable wormholes could never actually engender paradoxes, because any time travel situation turns out to permit many consistent solutions.
What does a consistent solution look like in this context? Does it mean the laws of physics would just conspire to prevent the paradox from ever happening?
That's exactly it. For example, if you tried to travel back in time and stop your parents from meeting, the laws governing the wormhole and the subsequent interactions might just make you fail.
Ow.
Maybe your gun jams, or you slip on a banana peel and miss the critical moment. The physics itself ensures that the time traveler's actions, no matter how disruptive they seem, are always contained within a consistent loop of cause and effect.
So the universe self-corrects against causal paradoxes at the most fundamental physical level.
It seems so.
Yeah.
It's a powerful and very stabilizing idea.
But even if the paradoxes are solved, we still haven't built a time machine. What's the fundamental physical barrier preventing us from forming a stable pathway for backward time travel?
The barrier isn't the paradoxes, it's the immense energy and curvature required. Thorne, working with Sungwon Kim, identified a universal physical mechanism that may always prevent spacetime from developing these closed, time-like curves, the pathways you'd need.
And what's that mechanism?
It's the explosive growth of the vacuum polarization of quantum fields.
Okay, we mentioned vacuum polarization briefly with LIGO, but let's dive deeper here. This involves virtual particles just popping in and out of existence in empty space, right?
It does. So imagine the throat of a wormhole. As matter approaches it and time travel becomes imminent, the extreme curvature of space-time near that curve would literally squeeze the quantum vacuum itself.
And this squeezing causes the virtual particles of the quantum foam to become highly polarized.
Meaning their energy density grows exponentially.
So the vacuum, which we think of as nothing, suddenly becomes filled with this massive growing concentration of energy.
A huge explosive back reaction. It's like trying to push a ship through a narrow channel, but the water itself becomes exponentially denser and more turbulent the closer you get to the pinch point.
This explosive growth of vacuum polarization creates a devastating shock wave
That destabilizes the wormhole and shuts down the closed, time-like curve before it can even fully form. It's a mechanism of cosmic censorship, and it's imposed by quantum mechanics.
So quantum mechanics acts as the ultimate time cop, preventing the universe from tearing itself apart.
That's a good way to think about it.
But the absolute biggest barrier to a traversable wormhole, the thing everyone talks about, is the requirement for the matter that actually props it open.
Precisely. This is the requirement for exotic matter. Working with Mike Morris and Ulvi Yurtsever, Thorne showed that traversable wormholes can exist only if they are threaded by quantum fields in states that violate the average null energy condition, or ANEC.
Okay, that's the phrase that tells us we're breaking the rules of physics as we know them. What does violating the average null energy condition really entail?
In simple terms, the ANEC is the physical law that says energy density, averaged over a large region, must always be positive or zero.
And violating it means?
It means the material you'd need to prop the wormhole open must have negative renormalized energy or negative mass density spread over a sufficiently large region.
We need matter that is universally anti-gravitating. It pushes space apart instead of pulling it together.
Yes. If it exists, it breaks every rule we understand about conventional gravity and energy. Thorne termed this universally anti-gravitating substance exotic matter. It exerts negative tension and a negative pressure, holding the wormhole throat open against the immense pull of gravity, which would otherwise just instantly collapse the structure into a black hole.
This sounds entirely theoretical, but is there any observed phenomenon in the universe that even hints at the existence of this anti-gravity element?
Thorne posited that this exotic matter isn't just needed for sci-fi staples like wormholes and warp drives. He theorized it's also what's necessary to accelerate the expansion rate of the universe.
So he linked it directly to dark energy.
He did. This links the highly theoretical wormhole requirements directly to the observed cosmological reality of dark energy. Because dark energy, which drives the current accelerated expansion of the universe, behaves exactly like a fluid with negative pressure. It fits the definition of exotic matter perfectly.
Wow. That is a staggering connection. The same bizarre physics that you'd need to hold open a stable portal is potentially responsible for the ultimate fate of the entire universe.
It connects the micro-scale quantum challenges to the largest cosmological structure we can see.
And while he was pursuing these grand concepts, he was also contributing to more practical relativistic theory. He and James Hartle derived the Hartle-Thorne metric.
Right, which sounds like a much more applied tool for astrophysicists.
It is. It's an approximate solution that describes the exterior of a slowly and rigidly rotating stationary body. It gives you the mathematical framework for accurately describing and modeling rotating neutron stars and other compact objects that aren't quite black holes. It's a key piece of practical math for any astrophysicist who studies pulsars.
And finally, his co-prediction of the Thorne-Durdkow objects.
With Anna Utkau, yes. These are hypothesized red supergent stars that have a neutron star core. Another example of him just pushing the boundaries of what general relativity allows in terms of stable, albeit very unusual, stellar structures. Thorne's legacy here is really defined by finding the absolute theoretical edges of possibility and just running headlong toward them.
Even if the required matter hasn't been empirically confirmed yet.
Moving on to part 5. Kip Thorne's incredible influence on culture and literature. He is such a rare figure who successfully transcended the purely academic field and became this force in popular science communication.
He really moved complex physics into the public sphere, like few others have.
His career started with foundational texts. He co-authored the 1973 textbook Gravitation with Charles Missner and his mentor John Wheeler, and that book is legendary.
It is. It's massive, it's complex, and it remains the comprehensive source for general relativity. It has inspired 2 generations of students, and it's considered one of the great scientific books of all time. So that shows his commitment to academic rigor from the start.
But the real turning point for the general public was his 1994 bestseller, Black Holes and Time Warps, Einstein's Outrageous Legacy.
Right.
That book didn't just summarize the science, it captured the imagination. It used analogies and storytelling to explain these incredibly dense topics, and it was published in 14 languages.
Absolutely. This ability to translate rather than just summarize, it really became his second career. Even after retiring from his main professorship, he stayed committed to fundamental education. He co-authored the massive graduate-level textbook, Modern Classical Physics, in 2017.
Covering 6 major areas, right? Optics, fluids, plasmas, elasticity, relativity, and statistical physics.
He maintained that commitment to rigorous teaching materials right alongside his public outreach.
And that public outreach is what most of the world knows him for today. His role as a Hollywood consultant, which all started with his friendship with Carl Sagan.
Right. He contributed ideas on the mechanics of wormhole travel for Sagan's novel Contact.
That was the prelude. The collaboration that really defined his cultural legacy was Interstellar. Thorne and his friend, the producer Linda Obst, developed the core concept for the Christopher Nolan film.
And Thorne didn't just, give his blessing and walk away. He served as the scientific consultant, working directly with the visual effects team and the director to make sure the depictions of the black hole, Gargantua, and the wormhole were mathematically derived.
He imposed rules on Nolan, didn't he? He insisted that nothing depicted in the film could violate currently known physical laws.
He did, even if the laws pointed to things we hadn't observed yet, like exotic matter. He introduced a key constraint. If something required violating physics, they had to be able to justify it with established theory, however speculative.
And this led to the creation of the most scientifically accurate black hole ever rendered for film. It was modeled based on Thorne's actual equations.
And he wrote the tie-in book, The Science of Interstellar, to explain exactly how they translated the field equations into those cinematic visuals and how the wormhole and the 5-dimensional tesseract could theoretically exist.
That's a unique accomplishment, ensuring scientific fidelity in a massive, special effects-driven Hollywood project.
And his relationship with Nolan continued. He advised the director on the highly complex time manipulation physics for Tenet.
And then later, he also advised the actor Cillian Murphy on his portrayal of J. Robert Oppenheimer for the film Oppenheimer.
Right, providing context on the scientific community and the intense pressure of wartime physics research. His influence on how physics is portrayed on screen is monumental. He helped move cinematic physics from simple hand-waving to mathematically rigorous speculation.
Beyond the blockbusters, he also maintained a visible presence in popular media. He appeared as himself in an episode of The Big Bang Theory.
And was featured in the documentary series The Craftsman. He actively shaped the presentation of these ideas. He proved that you don't have to sacrifice complexity or rigor to achieve broad popular appeal.
He took the often arcane field of general relativity and just made it a subject of genuine fascination for millions of people. As we wrap up this deep dive into the life of Kip Thorne, it's just impossible not to be struck by the successful duality of his career. He was both the rigorous traditionalist and the radical futurist.
That synthesis is the absolute core of his legacy. On one hand, you have the revolutionary practical work, the theoretical scaffolding, and the engineering blueprints for LIGO,
which solved decade-old noise problems using fundamental quantum concepts.
And that led directly to the Nobel Prize and the confirmation of gravitational waves.
And then on the other hand, you have the conceptual, boundary-pushing theoretical work, the intellectual architecture of black holes defined by pure geometry.
The hoop conjecture, the membrane paradigm.
And his rigorous exploration of time travel, which showed us that while we might not be able to build a time machine, physics itself contains these fascinating mechanisms to enforce causal consistency.
He successfully merged all these diverse fields, relativistic astrophysics, geometry, quantum mechanics, and engineering design, to really define the modern study of gravity. He took physics beyond Einstein's classical description and made it a truly dynamic, astrophysical, and quantum subject.
So what does this all mean for us, the learners? What's the final takeaway from the life of Kip Thorne?
I think he's a prime example of a scientist who actively fought for accessibility by collaborating with filmmakers, writing bestsellers, and tirelessly working to connect the abstract math to understandable physical realities.
He ensured that these profound, complex ideas moved out of the academic ivory tower and into mainstream understanding.
Exactly. He proved that the pursuit of scientific truth is intrinsically tied to the responsibility of effective communication.
And that leads us to our final provocative thought, something for you to mull over long after this deep dive ends. Our sources mention that, as of 2005, Thorne was intensely interested in one of the most fundamental mysteries remaining in physics.
The origin of classical space and time from the quantum foam of quantum gravity theory.
The idea of quantum foam suggests that at the smallest possible scales, the Planck scale spacetime itself isn't smooth at all. It's a frothing, volatile sea of geometry, constantly tearing itself apart and reforming.
It's a mind-bending idea.
So if the universe is fundamentally warped and frothing at the quantum level, how much of our perceived reality is truly classical?
And perhaps more thrillingly, given that Thorne theoretically quantified the geometric and matter requirements for things like traversable wormholes and warp drives.
The need for that universally anti-gravitating exotic matter.
Right. Are we currently looking at the cosmological evidence for it in the form of dark energy, the exact substance we would need to make his most outrageous theoretical legacy a practical reality?
Kip Thorne showed us where the edges of the universe lie, both practically with LIGO and theoretically in the pages of his textbooks.
The question that remains is whether the universe will cooperate and give us the tools we need to cross those edges.
A question only time, and perhaps the next generation of physicists that Thorne mentored will answer. Thank you for joining us on this deep dive. We'll see you next time.